Exercise 6.1, number 11, has us find the orthogonal complement, W perp, of a subspace W given as a span of these two vectors. Vectors with 4 components, so this is happening in R4. To find an orthogonal complement, we ultimately found the null space of a matrix. Let's take a look at the notes. And if we'll look at note 6.1a from the class notes, to find W perp, we must find a basis for subspace W. Got it. They actually gave us subspace W by giving us a spanning set. It was in fact a basis because there was only 2 vectors in it, so it must be linearly independent. Then part 1 here says we'll find a matrix A having as its row vectors the generating set of W, or the basis vectors of W. And part 2, the null space of that matrix will be the perp space of W. Okay, so let's do that. Okay, so we need to make matrix A with these 2 vectors as its rows. So let's document it. We're told by note 6.1.a to create matrix A with the spanning vectors, the generating set, it's also called, the spanning vectors of W as its rows. As its rows. All right, handful of times, a couple of times, we put vectors into a matrix as a rows. It was usually columns. We've got our reasons. We've got our dot product reasons for doing rows. Okay, so matrix A then would have as its first row 2, 1, 3, 4, and have as its second row 1, 0, -2, 1. Okay, so by the note we create this matrix. Next, find the null space of A, that is, solve the system of equations AX equals 0. That is what the null space was by definition. Okay, homogeneous system of equations, coefficient matrix A. And remember what we would do to solve this, or actually just to write this equation out, is we would put a column vector, x1, x2, x3, x4. We need 4-dimensional vectors here. And we do a row times column thing, row times column thing. And when you do that row vector times that column vector, you're taking a dot product of this vector first and this vector next with some unknown column vector x. You want that dot product to be 0, don't you? Because we're looking for a perp space. Dot products of perpendicular vectors are 0. That's why we're putting those vectors in as rows in that matrix A. So we'll take the augmented matrix. We'll take A augmented with zeros. Okay, that will be the given matrix augmented with zeros. We'll solve the associated system of equations. Okay, let's interchange the first and second rows. I want to use the 1 to do the arithmetic to avoid fractions. So let's take R1, interchange it with R2, giving us, let's see, second row becomes the first row. Whoops. First row becomes the second row. And we'll do our usual thing. I want to pivot. I want a nice pivot. That's why I swapped the rows. We got a nice pivot of 1, We'll use that to eliminate the 2. We'll put this in reduced row echelon form, which I think is about to happen in one more step. So to eliminate the 2 with the 1, we need to take row 2 and subtract twice row 1. Okay, doing that arithmetic produces, first row doesn't change. Second row, 2 minus 2 times 1 is 0. That's why we did that. 1 minus 2 times 0 is 1. Excellent. 3 minus 2 times negative 2. That's what, 3 plus 4? This is a 7. 4 minus 2 times 1 leaves us with a 2. And there we go, in terms of reduced row echelon form for the coefficient matrix. So this gives, so we're trying to solve a homogeneous system of equations. Of course, there's a solution. Looks like we've got 2 pivot-free columns. I think we'll have 2 free variables. Converting this back into equations, we're looking for components of vector x. So we treat the unknowns as x1. Let's see, we got 1x1, 0x2, minus 2x3, plus x4 equals 0, and x2 plus 7, x3 plus 2x4 equals 0. Or, as always, we want to write that as x1 equals, x2 equals, x3 equals, x4 equals. Then we'll introduce free variables, and then we got it. So this becomes, all right, looks like x3 and x4 will be free variables. The third and fourth columns are pivot free in the coefficient matrix, so that's how that's going to play out. Move this to the other side, we'll get 2x3 minus x4 for x1. For x2, we'll get negative 7x3 minus 2x4. X3, here's x3 is x3, and I guess x4 is x4. Yeah, those will be free variables. Okay, let's let R and S be free variables, x sub 3 and, and x sub 4. So let R equal x sub 3 and S equal x sub 4 be free variables. Then, continuing down here, simply rewriting this in terms of R's and S's, we get 2R minus S for x1, negative 7R minus 2S for x sub 2, R for x sub 3, and S for x sub 4. Or, if we'll write that as a vector equation, R and S are free variables, can be any real number, so we're about to get a span. If we'll write that as a vector equation, we'll get vector x equals, let's see, we've got R times, what do we get for the coefficients of R? 2, negative 7, 1, and 0, plus S times the coefficients are negative 1, negative 2, 0, and 1, where R and S can be any real numbers. Can they be 0? Sure. We're not doing eigenvalues here. I mean, we just did a bunch of stuff with eigenvalues and eigenvectors. Eigenvectors can't be the 0 vector. These are solutions to a system of equations, so we don't have that extra little piece hanging over our head. So, the null space of matrix A must be the span of these two vectors. So, the null space of A is the span of those two vectors. The null space of A is the span. Got a little stylistic concern here. You want these as row vectors, as column vectors. Well, let me just comment on it, and I'm going to write them as row vectors. And this should be as well the perp space of space W. All right. I guess the way the row times column thing works in the multiplication, probably the vectors in the null space, I should express those as column vectors. We got into this with a situation where they gave us row vectors, so I'm going to give them an answer in row vectors. So that style might be arguably a little bit sloppy, but the numbers are correct, and I would want to give an answer in terms of row vectors because we're asked a question in terms of row vectors. And there's the orthogonal complement. How are you going to give vector spaces? By expressing them as a span of something, by giving bases of them, or at least generating sets. That's a basis. I'm sure those two vectors are linearly independent.